You remember there was a day not too long ago when there were computers and there was communications, but they were distinct from each other. You'd actually go and you'd sit down at a computer and you'd do some work, but you had no expectation that it was connected to every other computer in the world. Maybe you had a personal digital assistant that you carried around with you in the palm of your hand, but it wasn't tethered to every other PDA, every other computer, to an internet. What is it that happened in the last decade or so that made it possible that information was everywhere? In the previous lecture, pair of lectures, we talked about how electronics has enabled computing, the processing of information at vast speeds and at low costs. Well, the internet is the communications side of that story. It comes down to our ability to send information and receive it with high fidelity and at very low cost per bit. How low is the cost? Well, back in 1971, if you wanted to send a terabit of information, a terabit is about 1,000 movies. It would be a couple of hard drives today. If you wanted to send that data over the network rather than sending your hard drive from Boston to California, it would have cost about $150,000 to do so. Today it costs about 12 cents. In 1930, if you wanted to pick up the phone and have a 3-minute call between New York and London, it would have cost you about $300 in today's dollars. Today that costs us about 20 cents. The key that we'll talk about today to realizing this incredibly low cost per piece of information, per unit, per bit, per binary digit, the key has been fiber optic communications combined with wireless communications. Now, we spoke during the previous 2 lectures really about the basis for wireless communications. This was our ability to make silicon circuits that were very low in cost, that got smaller and smaller, and that got faster and faster and more efficient in their utilization of electrical power. And so it's that success of electronics to microelectronics to nanoelectronics that's the basis for our untethered communications. But there's a backbone, an information carrying backbone that resides behind the mobile devices that we are all able to carry around with us and achieve continuous communication with. That backbone I'll call the optical internet. That refers to our capacity to send vast quantity of information down what you can think of as pipes for information, and the pipes carry light. So let's talk about these pipes. Let's talk about the optical internet. Here's a picture of a very familiar one of a bunch of optical fibers. So these are pieces of glass, and through each one is independently conveyed a stream of light, and the light is modulated. It's turned on and off, and through that on and off, and through a synchronous measurement at the other end with a detector, we're able to convey information. Now, the key to sending a lot of information per second is to modulate that light many times per second. We've seen these familiar pictures before, these glass fibers. I'd like to talk about how they work. What are their properties that are so important? What does that have to do with the materials, the atoms, the molecules that underlie them? But first, onto the structure itself. What does the pipe look like? Well, here's one of these pipes in cross-section. You can see a light ray, which is the red line, bouncing back and forth down this optical fiber. And this idea of bouncing ends up being very important. Light is prone to diffuse. It's prone to disperse. When you think of a spotlight, you have to work hard to try to focus it. But the further away you are from the spotlight, realistically, the more that beam is going to be spread out. But if we're going to communicate information from Boston to California using just one of these small glass pipes, we're going to have to confine the light. And so this is one of the first properties of optical fibers. In fact, we call optical fibers, based on this glass cladding and also a glass core, we call them single mode fibers because there's only one angle at which the light can bounce. We design the shape of this core, which is cylindrical, and we design the optical properties of the cladding that wraps around that core such that light propagates with only one bounce angle and consequently with a single speed, with a single velocity over these very long distances. How do we engineer that quality? Well, this is really all about creating an optical environment in which light has 2 options. It can either propagate or it can be lost. It can escape. And then our job in creating the source of light and shining a beam of light into one of these optical fibers is to excite only this one mode, only the light mode, where light can just race down this fiber without impediment and at a single well-defined speed. Imagine what would happen if light had a couple of options. Imagine if it could bounce at different angles and therefore make it at different rates. Our signal would disperse in time. It would spread out. And that phenomenon is known as dispersion. And if we're going to try to get as much information packed in as possible, we want to modulate our optical source as rapidly as possible. We can't afford any spreading. Spreading in time would be a loss of signal integrity. We would smudge our signal. We would no longer be able to resolve it. And so the design of fiber optic cables that achieve this very low dispersion is one of the central tenets of successful fiber optic communications. There's another really crucial aspect to the ways in which optical fibers have been designed and have been constructed, and that relates to loss. Clearly, to ensure that our signals go as long as possible without losing information, without losing power, we're required to make this glass as transparent as possible. There's a variety of mechanisms by which light can be absorbed really in any medium. So a first one is what we call band-to-band absorption. And by that we simply mean that the available electronic states, let's say in a semiconductor, those states cannot be successfully breached by light coming in, by a photon having a particular energy. If a photon can come in, shine on a material, take an electron, excite it successfully to a higher energy, if there's a shelf that can elevate that electron to a higher up energy level, then we will have absorption. Clearly that's not what we want if we're going to send information over thousands of kilometers. And so optical fibers are designed to have essentially no optical transitions or no electronic transitions available at the energies that we'll be using to send the information with. There's another way to lose light, though, that's not absorption. It's called scattering. And this is the phenomenon that we see in clouds or in fog, where light doesn't actually transfer its energy into the particles of water that make up a cloud or fog, but having this medium, which is a bit different from the air environment, having this little bubble, this little droplet of water suspended in the air, leads light to see a discontinuity and ends up with some probability being scattered in another direction. Well, that doesn't make seeing very easy. You can't see through clouds and you can't see fog as a result of the scattering, and it doesn't enhance the visibility of light going down an optical fiber either. So this is all about smoothness. This is all about, it's just like with the clouds. If we were to have an optical fiber that created a path that wasn't smooth, a bit like having a well-paved roadway, then we would have a reason why light could scatter out of its propagating mode rather than stay confined down the pipe. So making these interfaces in these glass fibers very, very smooth and perfect and well-controlled and very homogeneous, making the core material out of a single type of glass, making the cladding material out of a single type of glass, that is another one of the key steps in the development of optical fiber growth that was so crucial in allowing information to propagate such vast distances. Now, there's a particular wavelength of light, or range of wavelengths of light, that are particularly conducive to propagating down optical fibers without loss and without scattering. It really comes from a compromise. On the one hand, if you go to too short a wavelength, too high a photon energy, you're prone to participate in certain scattering and absorption processes. And if you go to too long a wavelength, you're prone to participate in other absorption processes, processes that are more like thermal processes, lower energies, but that can become very abundant once you get down to these very small energies. And so that drives us to kind of a compromise wavelength or a compromise photon energy. And at this wavelength, light can propagate for over a kilometer with almost no loss or scattering loss at all. It's pretty incredible. So imagine if you were to take, say, a window on your home. Is it maybe a centimeter, 2 centimeters thick? Well, imagine taking that window, and instead of it being a centimeter or two thick, it being a kilometer, almost a mile thick, and being able to see perfectly through it. That's what optical fiber technology has achieved for us. This incredible transparency is the basis for being able to convey information over such incredibly long distances. So now we ask ourselves, we have our window, we have our basis for confinement, we have our basis for sending information over these very long distances. Well, where will we get the light from? This light needs to have some very specific properties. But first of all, it needs to be something that we can couple into an optical fiber. These optical fibers, in order to achieve their single mode properties, in order to ensure there's only one available bounce angle, only one velocity for light, these optical fibers are quite small. They're about 10 micrometers in diameter. So they're not at the nanoscale. They're more kind of, they're on the optical length scale. But in order to couple into these, we need to make a beam of light that's similarly small. So imagine taking a light bulb that puts light everywhere. It'd be very, very hard to focus much of that light inside. Even with a light-emitting diode, it'd be very difficult to couple most of the light into this very small aperture. Lasers, on the other hand, are famous for having exactly the properties that we're looking for. Lasers provide a beam of light having a single direction. And so they provide us with the opportunity to couple right into this direction that the light will be propagating down in the optical fiber. In fact, their beams can be tailored such that the range of acceptance angles of the optical fiber can be matched by the output of emission angles from the laser. Now that's one sense in which light from a laser is sort of very pure, very perfect. It's the sense in which it's very directional. There's another sense in which laser light is very pure, and that's in the spectral sense. When we're thinking in our wave picture of electromagnetics, we would say that it's got a single wavelength. It's got a single periodic oscillation in time and in space. It's very pure in its spectral content. It would be like singing a single operatic note without any vibrato, a very pure note, very clean note. In our photon picture, in our quantum picture of light, we would say that these colors of light have a single well-defined energy. And that ends up being very important as well because, as I described, the low loss of the optical fiber derives in part from having selected a color of light that's very not prone to be absorbed. It's very unlikely to be absorbed. And so that point about the photon energy is extremely important as well. So this is what we desire. These are the properties of light that we're looking for. But how do we go about generating it? How do we go about building one of these lasers? In fact, if you were to picture a laser that perhaps you've read about or seen on TV, perhaps you've seen pictures of the early lasers that were developed in the 1960s using gases as the medium which transferred energy from the electrical domain into the optical domain. Or perhaps you've seen pictures of lasers that are going to be used to shoot down missiles, incredibly powerful large lasers. You'd think, this doesn't match with the size scale we're talking about. You think, you know, these optical fibers, I have this aperture that's 10 micrometers in size that I need to couple into. How am I going to match that with a laser? Well, it turns out that semiconductors, including semiconductors using quantum effects, that have components of them that are nanometer sized, the semiconductor lasers have been developed that are extremely small. They're extremely compact. They look a lot like very small chips, very small integrated circuits. And they use the semiconductor itself as the means of transferring energy from the electronic domain, where we're able to pass a current through one of these lasers, into the optical domain. This is how one of these lasers works. The lasers rely essentially on two phenomena occurring simultaneously. The first one is amplification. Amplification is familiar to us. For example, obviously your stereo speakers participate in amplification. They take a very weak signal, a little modulation in the electrical domain, and they turn it into first a much stronger electronic signal, and then that in turn is transduced into an acoustical signal. So amplification, of course, then refers to growing the intensity of signal, giving it more power, but retaining the underlying form of that signal, just amping it up, bumping up the intensity of that signal. So in lasers, the amplification that we're talking about is amplification of light. We're talking about taking a weak optical signal, and a weak optical signal can emerge anywhere at any time within a laser. It's called spontaneous emission, wherein light is always being absorbed and emitted. So there's always little bits of light around. But one of the key components of a laser is to take some of these little stray bits of light that are always coming and going in the real world at room temperature and gain them up, provide them with amplification. So we call this optical gain. That's the first ingredient in a laser. The second ingredient is a resonance. You can also think of this as feedback. In the simplest terms, the front and the back of a laser are both mirrors. They're not perfect mirrors. If they were perfect mirrors, then light generated between those two mirrors would always remain trapped. But if they're just slightly less than perfect mirrors, light is mostly trapped, and then occasionally it can escape out the front facet. It can be transmitted through the front mirror that has a less than unity reflectance. And so within this laser cavity, we have a photon occasionally being generated through a spontaneous process, amplification of that photon where its intensity grows. In fact, it turns into many photons as it propagates through, substantial reflection, and then back and forth as we build up and we build up and we build up this crescendo of light within our laser cavity. Now, eventually, we build up such a crescendo, such an intensity of photons within our laser cavity that the amount of energy we're pumping in electrically to create this gain cannot amplify further. And so we reach what we call a steady state. We reach an average expectation of a number of photons, of a density of photons inside this laser cavity. And while these lasers are very, very small, the length of their cavities are perhaps a millimeter, and their lateral dimensions are on the order of microns. The intensities locally within the most powerful of these semiconductor lasers are amazing. They're about the intensities of light inside the sun. And so within this very small device, we've built up an incredibly high power density using the combination of amplification or gain and feedback or resonance. Now inside this laser, there's some crucial nano-engineered components. In fact, this is the field that brought me into the field of nanotechnology. I was just an undergraduate student at the time. I was studying engineering physics or applied physics. And I loved my physics courses. I loved studying quantum mechanics, solving problems, solving equations. But I thought it got so much more interesting if I could actually see the manifestations of these very exciting, sometimes weird, sometimes unusual concepts that we've talked about together, if I could see them manifest in some kind of device, and where they weren't just present, but they were what we were using. They were what we were taking advantage of. Well, quantum wells, which are at the heart of most semiconductor lasers today, are examples of quantum engineering in order to make a better laser. Let's talk about how they work. So inside a normal semiconductor, the energies that are available, the photons, the energies of photons that can be produced, these energies are determined by the structure of the semiconductor. But that can be quite limiting. There are only certain colors that are available from a given composition of semiconductor. Now, as I described, in fiber optics, there's a very specific wavelength that is our perfect compromise that makes our glass window completely transparent over a kilometer's distance. We need to match that wavelength very, very well. And it's very difficult to find a semiconductor that matches it just right. But in quantum wells, we take advantage of the fact that the electron wave has a physical extent. It's a cloud, as we've discussed. And we compress it down just in the plane, just in one dimension, to make a confined structure which boosts up the energy of these electrons. We tune it the way one would tune a guitar. We tune the resonance energies that this electron wave experiences. And by tuning them just right, by pushing these energy levels up, we're able to achieve stimulated emission, the process of gain inside our laser, at exactly the wavelength that we need. And so through this quantum engineering, and only because of it, we're able to perfectly match the colors of light that are generated from a semiconductor with those that we desire to achieve extremely efficient, low energy, low cost per bit communications. It's also just worth mentioning that the semiconductors that we use here, they're semiconductors the way silicon is, but they're not silicon. There are materials such as gallium arsenide or indium gallium arsenide. Instead of residing in group 4 of the periodic table, where the elemental semiconductors such as silicon or germanium reside, these are called elemental because only one element, pure silicon, pure germanium, is required to make materials this way. They're in what are called the compound semiconductors. And with the compound semiconductors like gallium arsenide, we combine an element from group 3 and another from group 5. Gallium from group 3, arsenic from group 5. And we combine them together in equal stoichiometry. So thinking back to our periodic table, we've achieved a good match. Group 3 and group 5, they together will satisfy a full electronic orbital, the way silicon, 4 plus 4, will satisfy a full electronic orbital. They also rely on covalent bonding, so they're very, very strong. They're very robust materials. But by introducing another element, by having a pair of elements, or in fact, we can introduce a third or a fourth element from group 3 or from group 5, we have more degrees of freedom. We have more room to engineer the band gap of our semiconductor. So as a result of that, we're able to make materials that are much more agile. They're much more prone to enable us to choose just the right wavelength for the emission of light. But that point about which semiconductor we use in optoelectronics brings us back to a really attractive and exciting opportunity for the field of photonics, the engineering using light, which is researchers have made considerable advances in the last couple of years in figuring out how we could use silicon as an optical material. And that would be very, very attractive. These compound semiconductors that have been the basis for lasers and fiber optics, they work well when you're thinking of engineering discrete components. It's a bit like when we were talking in our electronics lecture about the original transistors, where even in the 1950s and 60s, people were starting to make very competent transistors that could switch, but they had a really hard time connecting them together. Well, the problem with these compound semiconductors is that typically their cost is much, much higher than that of silicon. A component of that is the actual materials themselves and their availability, but another is that silicon, because of the electronics industry, has scaled so much that there's now many, many ways, many different foundries in which to make silicon. And so there's a community of researchers and now companies that feel very strongly that if we could engineer optical materials and devices using silicon, we would be able to make the use of light in communications and potentially even in computing much more widespread. Well, why is this almost an inevitable trend, an important thing to do? We talked during our discussions of the field of electronics about how as we make our chips smaller and smaller, we put more and more energy density into a given region of that chip. In fact, it's amazing. If you look at the evolution of the energy density of integrated circuits, we're only a few doubling factors away from having the same energy generation density in the very most active part of an integrated circuit as the energy density inside a nuclear reactor. And so we're starting, as we shrink and shrink and shrink in the field of electronics, we're moving towards a denser and denser generation of energy. Now on our chips, of course, our goal is to whisk that energy away and to transport it away as quickly as possible so that our chip doesn't heat up and melt or start to lose performance. But one of the most energy consuming factors in the operation of a chip today isn't the computing, though that consumes energy too, but it's the communications. And so one of the reasons to be so interested in seeing whether we can integrate electronics, silicon, with optics is that we may be able to make the communications function much lower in its energy consumption by building it on top of a silicon chip. There's a lot of exciting work going on in exactly this area, and there's a couple of pieces to it. So one of them is to be able to guide light around a silicon chip in a manner where it's not lost. It's just like in the fiber optic case. And in order to do this, researchers have recently discovered how to use existing electronics processing, so things like photolithography and etching, which are already utilized to make electronic circuits. Well, they figured out how to make good waveguides out of silicon. And once they figured that out, they actually realized that silicon was an extremely good guide for light. It's almost more like a wire, a tightly confining wire for light than a fiber optic cable is. Silicon has a very high refractive index. In fact, this is a place where silicon has something in common with diamond. The appearance of diamond, the fact that it's got this beautiful ability to reflect light in many directions when you hit it, and yet it's transparent, that comes from its having what we call a very high refractive index. It's got a high optical density. Well, silicon does as well. And what that means is that if you can get light into it, which is the hard part with something with high refractive index, but if you can get light into it, then the light doesn't want to escape. It's tightly confined. It gets trapped inside. And it's that trapping and the multiple bounces that makes diamond have its characteristic flash of appearance. So in the case of silicon, what this means is that we can make waveguides that can meander across an integrated circuit, can take multiple bends, can go around loops, can go around tight turns, and they can do that very efficiently. And so silicon is proving itself out to be an extremely good mode of conveying light on integrated circuits. So that's looking very promising. Now, another problem, though, was with this high refractive index, it was hard to get light into the silicon waveguides. And there have been recent advances in the design of the regions where we couple light from the outside world into these waveguides called adiabatic coupling, where we kind of go continuously from the size and character of light in the air, and we funnel it down. And it really does look just like a funnel. We funnel it down into the silicon waveguide for convenient conveyance across the integrated circuit. There's another field that's attracted great excitement these days that doesn't even use an optical medium, one of these high refractive index media for the conveyance of light. The field is called plasmonics. And here, researchers are making metal particles that are spaced a defined distance from each other, where electromagnetic waves can hop from one particle to the next particle to the next particle. It's a bit like crossing a stream and having a bunch of evenly spaced rocks that you can use as steps along your way. This has yet to be fully proven out as a practical technology, but it's very much a nanotechnology because the steps, because of light's characteristic size, the steps themselves are measured in the kind of 50 to 100 nanometer range. These are actually the same particles that I was describing earlier when we were talking about stained glass. These particles that were, without even knowing that early artisans were introducing plasmonic particles into stained glass, they were doing so, and they were shaping the color that the glass appeared to have. Well, these same kinds of phenomena are now being used to provide a means of carrying light systematically around an integrated circuit. Where this is ultimately leading to is being able to convey light around the silicon integrated circuit. But the other piece of this is, just like in our fiber optic communications, the ideal thing would be to generate light and to turn it on and off right on the chip. And until about 5 years ago, we hadn't thought of silicon as being an active optical or an active optoelectronic material. It was one that could pass light through itself, but that was about it. But in the last half decade, researchers have found that they can now, using new phenomena, make lasers on silicon, and they can make modulators, which turn on and off optical signals. One of the missing pieces in this field of active silicon electronics is that at the moment, these components are a little bit big. So they end up taking up a fair amount of the real estate of the space on one of these silicon integrated circuits. So the thrust of this field now is to figure out how we can take these laser technologies and modulator technologies, which are now fast enough to be extremely useful in lowering the power burden in silicon integrated circuits, how we can take these new building blocks and condense them even further in order to scale down, just the way Moore's law enabled us to scale down the electronics. We need to proceed with scaling down the optics as well on silicon. In this field of optical communications, it moved so fast. We talked about Moore's law in the context of electronics, where there was this doubling every year. Well, in optics, in fiber optic communications, there was a doubling in efficiency, or in number of bits that could be sent per second over a given fiber cable, every 18 months. There was an even faster generation turnover. And at one point, when people realized they could put many colors, they could put a rainbow of colors down an optical fiber, there was just a sudden increase of a factor of 10, essentially overnight, with the advent of wavelength division multiplexing. It's these kinds of leaps and bounds advances that led to an optical internet where bits were nearly free. This field of optical communications, building the optical internet, connecting it to the wireless world, it's got a rich set of fascinating physics at the nanoscale. It involves light as a wave propagating down fibers, and it also looks closely at light as a particle, something where we generate in a fundamentally quantum device, the laser, a light that is not absorbed in the fiber and can travel many, many kilometers, in fact, hundreds, even thousands of kilometers, very, very long distances without losing its energy. This has also given us a chance to feature two of the stars of the show in nanotechnology, electrons that are the basis of computation because they love to interact with one another, and photons, which can propagate freely. And many of the devices that enable this are at the junction between the two. They're the ones that allow us to transduce between the electronic domain of the world of information and computing, and the optical domain, the domain of communications.